My name is Gautam. I am from Amrita Vishwavidyapeetham AIA Amaravati branch, 3rd semester. Today I am going to present and discuss about my topic, graphs and sparse matrix. Let's go into it. First, let us discuss about graphs. Graphs are a non-linear data structure and they can be defined as a set of vertices which can also be defined as nodes and edges. A graph can be defined like a set of vertices or nodes which are connected by edges. This here is an example. These three, 0, 1 and 2 are the vertices, while this here is the edge. There are two types of graphs, which are undirected graph and directed graph. Let's go into undirected graph. Undirected graph is a graph where the edge, which we use to connect the vertices or nodes, does not have a specific direction. It is unable to determine its source and destination. That is an undirected graph. Meanwhile, a directed graph is the edge has a specific source of direction. It is able to determine its source and destination. That is a directed graph. There are two ways in which we can represent a graph. The two ways are, one, in an adjacency matrix, and the other with the adjacency list. Using these two ways, we can represent graphs. In adjacency matrix, suppose the matrix has vertices of I, j, and it has n edges. If the matrix with vertices I and j has an edge n, which can be represented like if the matrix with vertices of I and j has an edge n, we can represent it with 1. And if this does not have an edge n, we can represent it with 0. And I forgot to mention that adjacency matrix represents graphs in booleans, which is in ones and zeros. This is the way we represent a graph with adjacency matrix. Let us take an example for undirected and directed graphs for adjacency matrix representation. Let us take an undirected graph. In an undirected graph, suppose this here is an undirected graph. Let us write with this in a row column representation as a matrix 0, 1, 2, 0, 1, 2. Here 0 has an edge with the node 1 and also has an edge with node 2. But 0 does not have an edge with itself. So we will leave the space empty. But for 1 and 2 nodes, which 0 has an edge with, we are going to write it as 1 and 1. Similarly, is the case with 1 and 2 nodes. One has an edge with 0 and one has an edge with 0 and one has an edge with 2. So 1, 1. Similarly, the case with node 2. Node has an edge with 1 and node has an edge with 0, but does not have it itself. So here it is 1, 1. Here we can write it as a 0 or we can leave it empty because it initially represents that it does not have an edge with itself. Similarly, let's take the same example with a directed graph. In a directed graph, we are not going to look just on the basis of an edge. We are going to determine and represent the graph based on if it has a direction or not. Suppose there is a representation of direction from 1 to 2. There is a representation of direction from 2 to 0. And there is also a representation of direction from 1 to 0. So, there is no representation of a direction from 0 to any node. Here, since 0 is not represented in direction with any node, the 0 row will be completely empty, none. But since 1 has a representation of a direction with 2 and 0, we are going to write it as 1, 1. Similarly, 2 only has a representation of direction with 0, so we are going to only write it as 1. This is how we represent a directed graph. We just do not look on the edge, we look if the edge has a direction. This is how we represent a directed graph using adjacency matrix. Now, before going into adjacency list, there is a type of graph known as a dynamic graph, which is a dynamic graph changes based on the environment. Suppose a dynamic graph is different from a static graph. A static graph remains unchanged based on any situations. Meanwhile, a dynamic graph keeps on changing based on the situation. And flexibility has always been a major drawback for adjacency matrix. Because if you want to represent a dynamic graph in adjacency matrix, you need to reshuffle the whole vertex, edge and nodes. Everything you have to reshuffle, which is be a big hustle and bustle for you. So that's the reason why to represent a dynamic graph, the best way to represent a dynamic graph is with adjacency list. Because adjacency list we can interchange with the arrays, and we can differentiate with each other, and it is far less complex to represent a dynamic graph with adjacency list than with the adjacency matrix. So now going into adjacency list. Adjacency list. We represent the nodes as a set of array. So let the nodes be 0, 1, 2, and let this be the graph. Let this be a representation for the undirected graph first. So this is the undirected graph, and here this is the array based on the nodes. Here, let's look at the neighbors. 0 has a neighbor 1 and 2. So here, this is the list. This is also the list. 0 has the neighbor 1. So we are representing here 1 with the array, and this is the list. We represent the neighbors in adjacency list for the graph. So here 0 has the neighbor 1. 1 also has the neighbor 2. So we can here represent it there 2. But 2 does not have another neighbor. These are the neighbors for 0. But there is no other neighbor. So here you can represent it as none. Similarly for 1, it has 0, it also has 2. But there is no other neighbor. So we can write it as none. Similarly is the case for 2. It also has 0 and 1. So this can be represented as none. This is the representation of an adjacency list for an undirected graph. Now looking into the adjacency list representation for a directed graph. Suppose the same graph has the similar directions, like 1 is in direction of 2, 0, 1 has a direction to 0 and 2 has a direction to 0. This is the directed graph. Then, now we should not only look at the neighbors. Now here we should look at the directions. 0 does not have any direction. So 0 can be it is null, completely null. It's 0. There is no neighbor here. But 1 has the direction to 0 and 2. So here we can write it like 0, 2 and then null, because there is no other direction representation. 2 only has with 0. So we can write it as 0, and then we can represent it as none. There is no other. So this is how we represent the directed graph in an adjacency list. An adjacency list is far less complex, and we can represent more number of graphs in adjacency list than in adjacency matrix. Because if the graph you are getting is a dynamic graph, means the dynamic graph will be keep on changing. So using an adjacency list is far more better, and it will be easier for you than an adjacency matrix. The real world, the graphs, they have a vast number of real world applications. Let us take a few examples. We can use them in discovering fraud calls. We can use graphs, and the graphs can judge based on the previous calls. It can identify if the call is a fraud or not. We can also use them in bioinformatics. In bioinformatics, the graph can they can differentiate between the previous data, and they can give you the current data values. And we can also use, the most prominent would be the social network, where in social network the messages keep on coming, the reels keep on changing. So there in social network we use dynamic graphs. These are the vast, there are many more representations. These are one of a few representations of a graph in real. Let us discuss about a sparse matrix. Let us take this matrix into consideration. Here the matrix is 1. This is a 3 cross 3 matrix. In a sparse matrix, zeros should be more than non-zeros. In this matrix, the non-zero elements are 3, while the zero elements are 6. 6 is greater than 3. So hence this is a sparse matrix. If it is vice versa, where the non-zero elements are greater than 0, then that would be called as a dense matrix. There are two ways in which we can represent a sparse matrix. The first one is 3-column representation. In 3-column representation, let us take a look at the rows and then at the columns, and then we point out in which row and in which column we have the zero values. The row indices mean the rows in which we have the values is, this can be 0, the row values should be represented as 0, 1, 2, same for the column 0, 1, 2. So let us take in which row, in the 0th row and in the 0th column we have the first non-zero value. So it can be written as 0, comma. Then in the first row, we have our next non-zero value. You can write it as 1. Then in the second row, we have a third non-zero value. We can write it as 2. Same for the columns. In the columns, similar to rows, we check in which columns we have the values. Here we have in the 0th column we have a first non-zero value. So 0. Again looking into it, in the first column we have a second non-zero value. Now if you go to the second column, we do not have any non-zero value here. The third non-zero value we have is again in the first column. So we write it as again as 1. The values are 1, 3, 5. These are the values. The second way in which we can represent a sparse matrix is compressed sparse representation, also called as CSR. In compressed sparse representation, the non-zero elements would be compressed, and it can be directly written as the rows would be 0, 1, 2, column would be 0, 1, 1, and then value would be 0, It's 1, comma 3, comma 5. In compressed sparse representation, we compress the non-zero values and we can directly obtain them without going through a large procedure like the column representation. This is how we represent a sparse matrix. The real world applications of sparse matrix can be like a market basket representation, where the number of elements, not the number of elements, sorry, the number of items you buy will always be less than the number of items you will not buy. So we can use sparse matrix to represent the number of items we buy in a market. And in a programming language, whenever you write a code on a sparse matrix, always remember that you should represent the number of sparse matrix in non-zero elements and not in zero elements, because the number of non-zero elements will always be greater than 0, which will require more memory allocation and more space. Meanwhile, if you use a non-zero element, it will require less memory allocation and the computational space and speed will be very much more. And that is all about my presentation. Thank you.